In this video, we're going to talk about residuals and squared residuals. Now, if you recall from the previous video, we did an example about the company GE, and we were modeling their profits. We had some data that gave their profits from the years 2003 to 2007, and we constructed two linear models that tried to fit the data. And the question you could ask is, which one fits the data better? Okay, now let's go up and recall what our data looked like. Okay, these blue dots represented the profit at different years. The point 3 here represents the year 2003, and so on. And we constructed this black line that went through these two blue endpoints here, these two data points, and the line had equation y equals 1.8x plus 9.6. We constructed another line by this green line by picking two other points. Okay, and we had a different equation, y equals 2.1x plus 8.2. Now the question is, which one of these lines fits the data better? Okay, what do we even mean by a better fit? Now, if you remember, we looked at this model 1.8x plus 9.6, and we guessed what the profit was in 2006 based on this model, and it turns out that what we got was, when we plugged in 6 in for x into this model, we got 20.4. So the actual point on this black line is 6 comma 20.4, but the actual data said that the profits were 20.8. So you're off a little bit. You're off by 0.4. In fact, if you take this number 20.8 and you subtract 20.4, you get 0.4, and that's what's called the residual at this 0.6. Okay, the difference between the actual data point, 20.8, and the data point on our model here, this black line model. Okay, so let's go back down and say one way to measure the amount of error in a model is to compute the difference between the actual profit, y, and the amount y hat given by the model, just like we were talking about. If the data point is x comma y and the corresponding point in the line is x comma y hat, then that difference between those y values measures the error in the model for that particular value of x. And that number y minus y hat is called a residual. And we could determine how well a line fits the data by taking the sum of the residuals, but there is a problem with this. The residuals might sum to be 0. Okay, we could add up all those residuals, but the residuals could be 0, which doesn't mean there's no error. It only means that the positive and negative errors, which could be quite large, cancel each other out. So if we go back up and look at this, this data here, maybe the residual here, when we take 20.8 minus 20.4, that's 0.4. But if we did the residual over here at 4, maybe it's negative 0.4. Okay, and 0.4 plus negative 0.4 would cancel each other out, and that's bad. So what we could do, we want to have positive residuals, so we could either take the absolute value, that's one way of doing it, or we could just square the residuals. Okay, and when you square a number, it will always be positive. Okay, in fact, that's really the remedy that we're going to do. So instead, mathematicians calculate the sum of the squares of the residuals to measure how well a line fits the data. A smaller sum means a smaller overall error and hence a better fit. Okay, now that all probably sounds a little bit confusing, but I think maybe an example will help clear it up a little bit. So let's do the example that we have been working on. It says the two linear models that we found for GE's profits were y equals 1.8x plus 9.6 and y equals 2.1x plus 8.2. And for each of these two models, determine the residuals, then square each of the residuals, and then take the sum of the squares. Okay, whichever sum is smaller, it means we'll have a better fit for our data. Okay, so in this top model, y equals 1.8x plus 9.6, we already looked at 6. When we plug in 6 for x, we got 20.4. Okay, so this point 6 comma 20.4 is the model point. The actual data point was 6 comma 20.8. Now if we take y minus y hat, that's 20.8 minus 20.4, we get 0.4. Okay, when we square 0.4, we get 0.16. Okay, now I've filled out the rest of the table. Notice I found all the squared residuals. Some of the residuals are negative, but when you square them, they're all positive. And then when I summed up all of these squared residuals, I got 5.04. So that's, in some sense, a measure of the error in our model. Okay, if we had an error that was smaller than 5.04, we'd have a better model. Okay, so let's check the next model then. Okay, now notice, by the way, in the previous model that the residual in the first point and the last point, it was 0. And that's totally expected because we constructed our data based on those 2 points. And the same thing will be true in this next model. We constructed our data based on these points. If you plug in 4 in for x here, that would be 8.4 plus 8.2, that's 16.6. So notice the error here is 0. The residual is 0. 16.6 minus 16.6 is 0. If you square that, you get 0. Okay, now if you take another point, if you plug in 3 for x, you would get 6.3 plus 8.2. That would be 14.5. And so if we do y minus y hat, that would be 0.5. And if you square it, you get 0.25. And as you can see, I filled in the rest of the data in this table. And notice that when I took the sum of the squares of the residuals, I ended up with 6.03. So that, again, is a measure of the error in the model. And notice the error is a little bit higher than in the model above. So the model above fits the data better. Okay, so what that's saying in a certain sense is that the model that we had at the top, that was the black line, that fit the data better than the green line model. Okay, the sum of the squares of the residual is less for the black line than for the green line. So it's a better fit.